Hi, welcome to Module 5, and this is to help you understand this adiabatic lifting. So as I increase my air parcel in its altitude, I'm going to decrease its temperature, and some different actions are going to take place. I'm going to play with those terms that we just talked about in the previous slide, which consist of dry adiabatic rate, and you can see that the dry adiabatic rate is 10 degrees Celsius every 1,000 meters. And then if I hit my lifting condensation level so that the dry adiabatic rate temperature and the dew point temperature are the same, so they are the exact same temperature, which means that water begins to come out of suspension. It no longer is gas, it becomes liquid or solid. I go into my wet adiabatic lapse rate, and that is 5 degrees Celsius every 1,000 meters, which means I will decrease 5 degrees every 1,000 meters in my temperature set. Dew point also has rates, and the dew point rate for the dry is 2 degrees every 1,000 meters, and for its wet rate it is exactly the same, because once I reach saturation, the dew point and the actual temperature point are exactly the same. Water's coming out of suspension at that point, so it's the same rate of temperature release. A great example of this is the mountain example, and it's basically a question of, if I start with one set of temperature, what would be my temperature and actions as I get on the other side of the mountain? This is a great example of what happens on the west coast of the United States. As the air coming off the Pacific comes and it hits and goes up and over the Sierra Nevada mountains, for example, they will rain out at the top of the mountains, and when they descend down the other side, they actually warm up because they're descending, right? The air mass is going down. And they dry out because they've rained out all their rain at the top of the mountain. And so I'm going to work through this problem with you, and we can see that on the base of my dosery page, I can see that my sea level temperature is 25 degrees Celsius, and my dew point temperature at sea level is 13 degrees Celsius, and you'll notice that I color-coded everything. So as I'm going up in my altitudes, we're counting by 500ths on my altitude on this side. All my temperatures are in orange, and over here I did my temperatures in orange to help us out, right? And all of my dew point and TD, that abbreviation, when you see it means dew point, are done in purple. And I'm just doing this to try to help us look at this cleanly and understand all my numbers. And I actually set these up as slides, so you'll see each page. So I'll just flick to my next page slide, and I already did the math, but I went up 5 meters, and they were tricky. They did 500 meters, and this rate is at 1,000 meters. So we're only going to decrease in instead of 10 degrees, we're going to decrease by 5 degrees. And my dew point, because I'm only going by 500 meters and this is 1,000 meters, I'm only going to decrease by 1 degree. So when I did my first set of numbers, I decreased by 5 degrees and 1 degree, and I'll correct that for the next slide. So going to the next slide, and you'll see I corrected my rates for you, just cleaned it up, and I did my numbers again. So I went from 20 degrees Celsius, I went up in altitude another 500 meters, so I decreased another 5 degrees, and I went up in altitude for my dew point another 500, so I decreased in 1 degree, and I have 15 degrees and 11 degrees. So if I was standing at this point on the mountain, it is 15 degrees Celsius, and the humidity is the dew point, sorry, is 11 degrees Celsius. Next slide set, I'm going to do my same decrease, but this is where everything gets kind of concise. So right here you can see it's 10 degrees Celsius, which means that I've hit my lifting condensation level, or my LCL, lifting condensation level. What does lifting condensation level mean? It means that I made the bottom of my cloud. So this is my cloud right here, right? So I've hit saturation. That means that from this point on, instead of using my dry rate, I'm now all wet, so I'm going to use my wet rate, which will be half of 5 degrees because this is at 1,000 meters, so it's going to be 2.5. So this one's going to go by 2.5, and this one's going to go by 2.5, right? And once again, once I meet them, once they're equal, because they're equal to one another here, they're equal, I will actually use the same rate up above. So I'm going to go up by 500 meters. And once again, lifting condensation level is the base of the cloud. If I was to ask you in the previous problem, where does my cloud begin? My cloud begins at 1,500 meters. If I was climbing the altitudes of this slope, when will I reach the base of the clouds and I cannot see the top of the mountain? At 1,500 meters in altitude. So, drew in my cloud on my little slide, and I went for my next number, which is a wet rate. And so I subtracted 2.5 for both numbers, and I've got a temperature of 7.5 degrees Celsius, and my dew point is also 7.5. And I'm going to do that again because I'm on the windward side of my mountain, and so 2.5 again for my 7.5, and I'm at 5 degrees Celsius. Now, I'm on the windward side of the mountain. I have formed this lovely cloud, but the air mass itself is being held down to the Earth's surface by gravity, which means that once it gets over the top of the mountain, it's going to drop down. It also means that all of this water vapor has been condensing on condensation nuclei as it rises up. And so I end up with a big cloud, and I'm sorry, my cloud is a little confusing because all of this would be a cloud since I've met my dew point temperature, and I've also had precipitation occur. So this is the rainy side of my mountain, right? That all the rain is happening on this side of the mountain. Now I'm going to go up and over the mountain, and I'm going to dry out. So I'm going to go from my wet rate. So this is wet rate. Wet rate was from this point on. This was all the wet rate area. And I'm going to begin going back to my dry rate on this side of the mountain. This was dry down here. So dry rate, dry rate, all the way down the mountain. And started working on my numbers. Now notice I go down by 500 meters on this side. So I'm going to increase my temperature on this side by +5 on this one. And my dew point I'm going to increase by +1 because I'm dry. I'm going back to my dry rates. Now they're tricky because they jumped an entire 1,000 meters. So instead of using my 500 meters for 5 degrees, I'm going to use my 10 degrees for my 1,000 meters. And so I'm going to increase by +10 on here and +2 on that side. And last but not least, I'm going to increase by +10 and +2 on this side. And we'll notice that there's a distinctive difference right off the bat as we're working with our numbers here from one side to the other. I can see that the temperature is much, much warmer on this side. So this explains rain shadow deserts. And my dew point is very decreased. I'm not as humid. I don't have as much moisture. I'm not as wet on this side of the mountain either. So both of these things matter to the explanation of rain shadow deserts, and this little problem is a great example of how I use the adiabatic pressure numbers and these rates to solve a problem or explain this problem set. And once again, dry adiabatic rate is the rate I use when I am not equal to my dew point temperature, and I want to use the rate for both the dry adiabatic rate for temperature and the dry adiabatic rate for dew point temperature and work my problem. And then once I hit my lifting condensation level, which is the base of my cloud, it's also the point where dew point, TD, is equal to temperature. They are the same at this point. That's where the base of the cloud will form, water will come out of suspension, and I will make my ice crystal nuclei, or my condensation nuclei will begin to have water stick to it, and I will have my wet rate begin. Once I lose that moisture to precipitation, I will dry out, and I can sink using my dry rate. So, great example of this process. I hope this helps explain it so that you can understand both the terms and how I utilize these actions of these terms within a problem.